You there yet, Austin? Austin, if you're there, type something in the chat so I know you're there. Or Ethan. Sorry. All right, so let me see. You've got a function increasing from 0 to there and from 0 to 1/4, which is what I've got, and decreasing from, okay. So relative max, relative min. This is what it means by increasing and decreasing. What this means is when I'm looking at my number line here on my first derivative test, this plus means I have a positive slope. So you go back to algebra 1, positive slope looks like this. And then when you get to 0, you have no slope, and then you're going positive slope again. Then we get to 1/4, and we're going down like this. So define relative max and relative mins. If you look here, this right here, it's not a max or a min, because a max or min means it has to have what's called a change in concavity. It means the graph has to change its shape. But here at 1/4, it's going up and then going down. So that has some sort of change in concavity. So this right here would be a relative max. So you're going to have an x value of 1/4, and then when you plug it back into your whatever your position function was, which I think would have been x cubed minus x to the 4th, 3x to the 4th. Do a quick integral in my head. That should be right. 3x squared. Yeah, so you plug your 1/4 back into that, and you get the y value if it wants to point. But that's the relative max, relative min. But because this one is going something like this, it's not a max or a min. It has to look something like this for it to be a max, or something like this to be a min. So these are what these increasing and decreasing, these positive and negatives tell you. That's why I like doing the first derivative test on this, is because it can show you where your relative max and relative mins are. So what else, dude? So I think on your problem, the relative max, let me look at it again. The function has a relative maximum at, that would be does not exist. And well, no, the max is right here. So relative max at 1/4, this is your max. And a relative min does not exist unless there's another change somewhere. But if this is your original function, this is the correct derivative, then your points at 1/4 and 0 are right. So yeah, the min would be does not exist, because there is no minimum on this one, because the graph's going up, 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 up. Now it'll have a absolute minimum, but not a relative minimum. Yeah, if I had to guess, this graph probably looks something like this. something like that. Let's see. X cubed 3x fourth. Pretty much spot on. Okay, that's fine. I'm not going anywhere. How does the Y scale? Y scales all types of. Let me know when you're good. Zoom in again. Yeah, this little hump right here is not as profound on the graph, but if I scaled it right, it's gonna have like a little bubble right here. It looks something like this, like an itty bitty little dimple right there. General rule: when they give you a fraction, you give your answer in a fraction, but I don't know the program you're using. So if that's what you get, just do math enter enter. 0.0075 math enter enter. 3 over 400. Well, yeah, that's a general rule. That was a standard rule in my class. If I give you a fraction, you give me a fraction answer. If I give you a decimal, you give me a decimal answer. Oh wait, probably not in your class. You were my first year teaching. Wait, was Ethan first year or second year? Second year. I think Ethan was second year. But that's the idea behind relative mins, relative maxes, is looking where the changes, where the increasing, decreasing changes. It'll tell you if it's a max or a min. Oh. 1 over 256. But the 1/4 is right? Oh, did you put it back in the position function? You have to put it in the position function. So it would be 0.25 cubed minus 3 times 0.25 to the fourth. Math enter enter. Yeah, it's 1 over 256. You put it in the wrong function. Yeah. So here's what you did. I bet you put it in this function here. This is your velocity function or rate of change function. This is your position function. And because you're looking for a y value, you have to use your position function. So you put the 1/4 back into your original equation. 1/4 cubed minus 3 times 1/4 to the fourth. So when you're looking for an x and y value, you have to use your position function. When you're looking for max and min, you use the first derivative with the increasing, decreasing, because you want a position. So your position function is always your initial f of x. So the rule is on this is your f of x. This is a position function. This tells you where it's at, like the x value, the y value. Your f prime of x is a velocity function, which is a rate of change, which is slope. And then your f prime prime, I don't know if y'all do that, f prime prime, this is an acceleration function. Basically telling you how fast you're speeding up and stuff like that. So that's why you probably put it back in here and got that 1 over 400 because you were actually doing a velocity. You need to do the position with the regular f of x. So you mean that's what you did? You put it back in the derivative, or you put it back in the position function? Because when I put it in the position function, I got 1 over 256. I'm guessing you're good on the... Yeah, you can't put it in the derivative. You've got to put it in the position function. I guess you're good on the second derivative test. Believe it or not, you already have the answers to where the change in concavity is concave down at 1/4, 256. Because of this. This shows you all that. This, doing the first derivative test this way, actually shows you a lot of stuff even on the second derivative test. And yeah, that's all you do. I mean, this derivative's easy. To get the second f prime prime of x is just 6x minus 36x squared. Set it equal to 0. Solve. You still have 0 and then whatever the other number is. And I'll tell you where everything's changing. Pretty easy stuff. Well, yeah, I can remember getting the position. This is really helpful to know position, velocity, acceleration. I don't know how much you're going to use that in business, but that comes up a lot in physics. Because if you know the velocity of something, you can find the position of it by doing an integral. If you know the acceleration, you can find the velocity and the position by doing integrals. So not terribly bad. Would there be 2 concave downs? I don't remember the second derivative test off the top of my head. But we have 6x minus 36x squared equals 0. We've got x, and this is 6. Well, let's do 6x, and this becomes 1 minus 9. 9 times 6 is not 36. That's 4. And then you've got x equals 0, and then this is going to be x equals 1/4. Now, this right here, this spot at 0 on the first derivative, it's going to be inconclusive when you do the second derivative test because there's not actually a change in concavity. There's only one change in concavity, and that's at the 1/4 because it goes from increasing to decreasing, so it's going to change in concavity. So just one concave down. This should be inconclusive. If you look at your notes or in the book where it gives you the second derivative test, if you do that, you're going to have either it's concave up, concave down, or how do they word it? I literally just said it, inconclusive. So this test should be inconclusive because it doesn't change in increase or decrease. There's no concavity change. Man, I hope I get to teach AP Calculus next year. This is so much fun. There's so many little nuances to this. So many. I hope the class makes. Oh. Would there be a new point of inflection? No. The point of inflection is where the graph actually will change in concavity, or it does this weird little bend in it. Because simply, if you still set this equal to 0, you still get your 0 and 1/4. Yeah, they're going to stay the same. Your points of inflection are going to stay the same. It's amazing how much you get off of this first derivative test done this way. You get a ton of stuff off of it. Ugh. I'll tell you what, I'm blowing up on YouTube. I have 124 subscribers now. Yay me. You know, just like another 970 something. You send me something, Ethan? Yep. Let me look. Select the appropriate graph. Huh. Well, look at what I've done. Look at this right here. I said this is about what the graph's going to look like, because if you look, it's increasing, increases. It dimples out, then it's still increasing, and then it goes back down. So their scales are really small. Oh, I know what they meant by concave down. Yeah, because the graph is this way and this way. That's why there's two concave downs, which you should see it right there. My bad on that one. Been a while since I've dealt with changing concavity, so. And 1/6. Oh, I factored wrong. This should be a 6. This should be 1/6. Duh. Yeah, I factored wrong. 6 times 6 is 36. This should have been a 6, so this should have been 1/6 right there. Bonehead, basic algebra mistake. This is supposed to be a 6. That will make that 1/6. And then you just plug it back into your position function to get the bonehead. But yeah, here's what the graph would look like. I was pretty much spot on. Oh, silly, silly me. I know 36 divided by 6 is 6. It's not 4. But yeah, when you're finding points, make sure you use the position function to find your y values. So Ethan, does it let you do the problems again? Yeah, we can try one more. Let me erase. If you just tell me what the original position function is, the problem's going to be the same type. I don't know if you can see the paper flying while I erase. Yeah, let's do this. Most definitely. Let's do this. I'll start here and work my way that way. Let's do pink. Hold on. So that's the function we have. F of x equals x cubed minus x to the fourth. So we're going to know we need to do the first and second derivative. So I'm just going to do those real quick. So my first derivative is 3x squared minus 4x cubed. And my second derivative, wow. So my second derivative is going to be 6x minus 12x squared. All right. I don't know what all it asked. It asked to find the vertical and horizontal asymptotes. Right off the bat, there are vertical asymptotes. So my vertical asymptotes does not exist because this is not a rational function. So there's no vertical asymptotes. There's no horizontal asymptotes on this either. Shouldn't be. No horizontal asymptotes. Limit as x approaches infinity. Yeah, there shouldn't be any horizontal asymptotes on this either. You can double check on that. I'm a little rusty on that part, but this is not a rational function, so horizontal asymptotes, there's nothing to compare to the denominator. Very straightforward. As far as I'm concerned, horizontal asymptotes does not exist either. This is just a polynomial. Polynomials don't have vertical and horizontal asymptotes. Hey, that's correct. Okay, so here's the first derivative. Let's find our critical values by setting it equal to 0. Factor out a GCF. 3 minus 4x. Set them both equal to 0. And I've got x is going to be 0, and this is going to be a 3/4. All right, so from there we can do my first derivative test. I'll put 0 here and 3/4 here. Pick a number smaller than 0, pick a number bigger than 3/4, and pick a number between them. So let's do 1/2. I'm not calculating this in my head, so I'm just going to clear everything out. Let me put all these in here. X cubed minus x to the fourth. There's my position function. 3x squared minus 4x cubed. There's my first derivative, and then 6x minus 12x squared. There's my third derivative. Okay. So let's plug -1 in, and this should be positive 0.5. This is positive, and then 1 is negative. So same scenario as before. Graph's coming in like this, flattens out right here, then it goes up again, flattens out at 3/4, and then comes back down. So same idea. So we know the relative, there is no relative max, because relative min, no relative max, relative minimum, geez, because there's nothing that goes this way. It's not going from decreasing to increasing. It's going from increasing to decreasing. So it's a relative maximum. It's going to be at 3/4. So my relative max is going to be at 3/4, comma, and then, so we'll do 0.75, roll over, it's at 2.25, (9/4). So there's your relative max. There is no Yeah, there is no relative min. All right, that's easy enough. Now we do our change in concavity. We're going to take the second one. We're going to do 0 equals 6x minus 12x squared. Factor out a GCF, which is going to be a 6x. This gives me 1 minus, let's make sure I do my math right, 2x, which then we have 6x equals 0. And then, let's see, 1 minus 2 x equals 0, so we have x equals 0 and 1/2. At this point, there's two places where you're going to have a change in concavity because that's where it got us last time. It's changing here and it's changing here. So we know 0, if I plug it back into my position function, I have 0, 0. And if I plug 1/2 back into my position function, wait, I think this one's wrong. Yeah, that one's wrong. This is wrong. I plugged in the wrong function. So 0.75. I can quit bars into 1 here, 0.75. Math. This should be 27 over 256. Because if I take the 3/4, plug it back into my position function, this is what I get. Yeah, so these critical values, if I need to find their point, I'll put them back here. So I know I put them back into the position function, the original f of x. So we have 0, 0. So at this point it's 0, 0. This one here is 3/4, comma 27 over 256, because you want to use the position function, the original f. So this is your position. This is your velocity. And then this is your acceleration. That's how I'd remember them for physics. So position, anytime we're looking for an x or y value, we go back to the original f of x. This one's telling us where we're going to have a rate of change or a change in slope, the velocity's rate of change. And then the acceleration is going to tell us our change in concavity. So to get to 0, 0, because I got 0 here, I put it back in the original position function to get 0, 0. I put 1/2 back into the original parent function. So we're going to go bars, y bars. And that's 1. And we're going to do 0.5, which then gives me math, enter, enter. So this becomes 1/2 and then 1/16. So both of these, at both of those points is where it's concave down. And then let me look at the picture you sent me before. Concave down from 0. Function is concave up. 0 to 1/6. That's weird. Let me look up the second derivative test. Give me a second. I don't remember that one off the top of my head. Just show, I don't need a video, just show me the actual test. All right. So suppose f of x is a function x is twice as stationary towards x naught if the second derivative of x naught is greater than 0. F is a local maximum if f is less than its minimum. Which this is greater than 0. Yeah, this shows me it's a local minimum. Weird. Well, it's increasing from negative infinity up to 0. 0, it's not increasing or decreasing, and then it's going to jump from 0 all the way up to 3/4. That's where it's increasing. It's decreasing from 3/4 out to infinity. This is going down here. So increase, no increase, increase, and then it's decreasing for the rest of the graph. So your graph still kind of looks the same. Something like this. It's got a little dimple, then comes up and then back down. Something like that. Well, that's for multivariable. That's why that looks funny. Right. Wants a weird answer like this. Let me look. Oh, okay. Well, this is interval notation, so we can do, it is x is going to be less than 0. That's this part. This is x is less than 0. And then 0 is less than x is less than 3/4. So these mean the same thing. Yeah, if you remember, this is interval notation. This is just part of set notation. It's just lazy set notation. And then this is 3/4. My x is going to be greater than 3/4. Yep. Same thing, just different notation. Interval notation to me is easier when you're dealing with increasing and decreasing. Oh, really? So it's concave down here, and it's concave down here, and it's concave. So it says concave up. X is yeah, that looks okay. From x is not, yeah, it's just less than, it's not less than or equal to, it's less than 0. And then from 0 to x to 3/4. Yeah, that looks fine. Did not like the answer? Got it. Got it, got it. So, put it in. Ethan, I just read up on concavity change up and down. I don't know why I didn't remember this. This is not that hard. Nah. Wait. Right. I don't know then, dude. Me not know. Let me look at the graphs. I couldn't tell you because I mean I know what the graph's doing and it's increasing, then decreasing. Let me look. (27/256) or oh no, your critical numbers are 0 and 3/4. The 27/256 is the y value for the 3/4. That's where you're off. Yeah, your critical numbers. It should be 0 and 3 divided by 4, not 27/256, because 27/256 is the y value of the 3/4. Are you picking sticker burrs off him? Yeah, your critical values are here. These are your critical values. Ugh. 6:30. X is less than, yeah, you're decreasing from 3/4. All the numbers greater than 3/4 is decreasing. Yep. Yeah, that's what I have here. From 3/4 going down, it's all decreasing. Alrighty. I think I got pretty much the rest of the work here. All right, so if you look on the first derivative test here, same scenario as the other problem. Right here, it's going to be inconclusive because it's going from increasing to nothing to increasing. So it can't be a max or a min, because for it to be a max, it has to have something like this. For it to be a min, it's something like this. If you have something like this, it's inconclusive. So it's inconclusive at 0, but it has a maximum. If you look, it's going from increasing to decreasing at 3/4. So the actual point for it, where it's going to change from increasing to decreasing, is at that critical value 3/4. We take that 3/4, we put it back in our position function, and we get the y value of 27 over 256. So there is no minimum on this, but there is a maximum, and the maximum occurs at the x value 3/4, the y value of 27 over 256. And that's your relative maxima. Yeah. Wow, that is spot on for the graph. April, how much more does he have? You about done? I figured with that mower, he would have hacked it all out. Oh, but he's done the mowing part. Yeah, that's true. Let me know anyone else. And where does it concave up and concave down? Okay, so when I was reading on the concave up, concave down, let me flip back over to it. So it says when the function y f of x is concave up, then the graph of its derivative f prime of x is increasing. So I'm going to graph this and look to see where it's increasing, which would actually be here. Curious on something. So it's where it's increasing. I'm curious if I could do the same thing for the second derivative test. All right, so it is concave down everywhere where the graph is decreasing. So it's decreasing from negative infinity all the way up to 0. So I just graphed it to look. But I'm curious if I could do it this way. The same idea. 0, 1/2. So I do 1/4. Do -1 and 1. I don't know if this is going to work, but from negative infinity to 0, it is decreasing, which means it is concave down. Then it's concave up, according to this, from 0 to 1/2. And then it would be concave down from 1/2 going down. I am curious, though, just to see. Negative. Away. Positive. Give me a second, Ethan. I'll look at your pictures. And that's negative. So here. Wait, no. Here. 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 Oh, let's look at your pictures. Concave down when x is less than 0. And x is greater than 1/6. So this will be concave down is, yeah. Look, your concave down is from negative infinity. So this part right here, which I plug it back into position, I get 0, 0. It's concave down, x is going to be less than 0. And here, x is greater than 1/2. Those are your concave downs. Another way you could see it is if you graph the derivative function and just look to see where that's actually increasing or decreasing. If it's decreasing, it's concave down. If it's increasing, it's concave up. So I guess this would technically be concave up between 0 and 1/2. Concave up. That's right, concave up. Yeah, so it's concave up. So this is down. And then the up is going to be from 0x to 1/2. So it's concave up from 0 to 1/2 and concave down when the numbers are less than 0 and greater than 1/2. You can do the same idea right there. I didn't know that. Works out beautifully. It just makes sense. If that was a position function, then that would be that just makes perfect sense. So how would I find? So the points of inflection are here. These are the values in which I set the second derivative equal to 0. So if 0, put it back in the position function, I get 0. The 1/2, I put back in the position function, I get 1/16. And then, so those are the inflection points. So how would I find the up? Is that x is less than 1/2. Right, x is less than 1/2, but it's also greater than 0. So this is your concave up. This is your concave up, and these are your concave down. That would span the entire graph. So I don't know if it wants points of inflection. Here it says points of inflection. On the previous one, did it have both points in there? Like 0, 0, and 1/2, 1/16, or did it just have the x values? I don't remember. Trying to see, does it want the x values or the points? Oh, it wants the actual points. So you would type in 0, 0. You would type this in for your inflection points because it says points, not x values. So the inflection points, which has to have a point by definition, has an x and y component. You need to put both of them in. So these are your inflection points. Codes, what you doing over there, buddy? I think from there it's just a matter of picking the graph, and we already know the graph's going to look something like this. Yeah, all right, so to summarize this, we start with a f of x equals x cubed minus x to the fourth. It asks for horizontal and vertical asymptotes. Those aren't going to exist because this is a polynomial, not a rational function. A rational function would have a horizontal and vertical asymptote. Now, to find where it's increasing and decreasing, we're going to take my f of x, and I'm going to do the first derivative, so we get f prime of x, which is 3x squared minus 4x cubed. To find where it's increasing and decreasing, we want to find out where slope is going to be 0. So we're going to take the first derivative, set it equal to 0, and solve. From here, we just do basic algebra 2 stuff, factor out a GCF, zero product property. We find that our critical values are at 0 and 3/4. That means at those x values, the slope is 0, meaning it's neither increasing nor decreasing. I do the first derivative test. I put this on a number line, 0 and 3/4. I pick some test values, a number smaller than 0, and a number between 0 and 3/4, and a number larger than 3/4, which I pick -1, 1/2, and 1. I take these and I put these test values in the derivative to see what's actually happening with the slope on the graph, and I find out from -infinity up to 0 that slope is increasing. 0, the slope is 0. That's what we did here, and then after 0 all the way to 3/4, my slope is also increasing. At 3/4, the slope is 0 again, neither increasing nor decreasing. And then after that, it decreases because when I put 1 in, I get a negative number, meaning I'm going to have a negative slope. So those are my critical values. To find the relative max, relative min, all I do is I look here and see, you know what, right here, there wasn't a big change from a positive to a negative. But from a positive to a negative right here, it's going from increasing to decreasing, gives me a relative maximum. So to find the point in which I actually have that relative maximum, I take my critical value, 3/4, and I plug it back into my position function and evaluate, and I get 27 over 256. So this, at this point, is exactly the highest point on this graph, which is a relative maximum. All right, from there, it wants to know about concavity and inflection points. So we have to do the second derivative. So I go from the first derivative, and I take another derivative, and I get the second derivative. My inflection points, I just simply set it equal to 0 right here. I get 0 equals 6x minus 12x squared. Once again, do some algebra on there. Factor out a GCF, zero product property by setting them equal to 0, and I get x values of 0 and 1/2. To find the actual inflection points, what I'm going to do is I'm going to take the 0, put it back into my original function, my position function, and I get 0, 0, and I put 1/2 in here, and after evaluating and reducing the fraction, I get 1/16. So here are my two inflection points. Now, to check for concavity, what it actually does is if you know the graph of f of x, everywhere where the graph of f of x is decreasing, it's actually concave down, and everywhere where it's increasing, it's concave up. My critical values, or where I'm going to do a test on, are my 0 and 1/2, which I did here. And then once again, I pick test values, and I plug in -1, and I plug it into my derivative this time. And once I plug it in my derivative, I get a negative number. Then I get a positive number when I put 1/4 in there, because I have to pick a number between 0 and 1/2, and a negative number from 1. So since the graph of f, the derivative of f of x, is decreasing from -infinity to 0, that means it's concave down when x is less than 0. Also, since from 1/2 the derivative graph is actually decreasing, that means it's also concave down when x is greater than 1/2. But it's increasing from 0 to 1/2, so that means that the graph's going to be concave up. So my interval which it's concave up is between 0 and 1/2. And then from there, you pretty much have everything you really need to be able to figure out the graph. It's coming from -infinity, it's increasing all the way up to 0. Then it's kind of bending upward, which is a concave up, from 0 to 1/2. Then it's going back down, concave down, and it's going all the way down to infinity for decreasing. So you have your increasing and decreasing ranges in there. I mean, everything is all right there. You know what the graph is doing. I'm surprised it didn't ask for the x and y intercept, to be honest with you. But yeah, that's a summary of this whole problem. Summary of the whole problem. The y-intercept's easy, it's 0, 0. X-intercept's a little bit more tricky. Not really. It'd be 0 and 1. Yeah, 0 and 1. All right, you good, Ethan? Good? Took an hour. Boy. Had to review the second derivative. I actually understand the second derivative now better than I ever have. That's actually pretty easy. All right, cool. I'm going to end the stream. If you have another question, just shoot it over to me. If it's something short, or something short, I can make a quick video and just post it to the YouTube channel. If it's something long like this where you have to ask a lot of questions, sending me stuff, maybe do a quick stream. Well, 57 minutes isn't quick, but all right, dude. I will talk to you later. If you need help, you know where I'm at.